let's talk about your can optimization project. Say we have selected a can of our favorite energy drink, and classically, energy drinks are long and tall. The first thing we want to do is measure the diameter of our can, and we're going to do that to the nearest tenth of a centimeter. And when we measure across this can here, we get 4 centimeters, which of course means our radius is 2.0 centimeters. We want to keep that in mind, and we want to round everything and report everything to the nearest tenth. Now, if we measure the height of this can, I'm getting a little ridiculous here, but I'm going to call it an exaggerated 20 centimeters. So I know my actual radius of my original can is 2.0 centimeters, and my actual height of my original can is 20.0 centimeters. Now, the area of the can, the amount of material we use, is going to be the circle at the top and the circle at the bottom. So the surface area here is going to be pi r squared plus pi r squared. If I consider the sides of the can and I unroll the sides of the can after splitting it, that will reveal a rectangle whose one side is h, which we know to be 20 centimeters, and this part here went around the top and the bottom of the can, which is a circle, and we know the circumference of a circle is 2 pi r. Now, the rectangle's area, or the surface area of this rectangle, will be 2 pi r times h. So I can add that here, 2 pi r h. So my surface area of the can, when I simplify this, will be 2 pi r squared plus 2 pi r h. And if I'm looking for the original can, its surface area will be 2 pi 2.0 squared plus 2 pi 2.0 times 20.0. Those are centimeters. So in squared centimeters, I'm going to get 276.5 cm squared for, don't forget, this is the original can's surface area. Let's label this the original can surface area. This is the original can surface area. Well, let's find the original can volume. The volume is going to be the area of the top of the can, which is pi r squared, times the height of the can. So that's our formula for the volume of the can. Here's our formula for the surface area of the can. And when we plug in a 2.0 for our R value and a 20.0 for our H, the original can's volume to the nearest tenth is 251.3 cm cubed. Now, our question is this. Given that we are constricted by the actual amount of aluminum that went into the can, which was 276.5 cm squared, can we design a can that has more volume? In fact, we're not just interested in more volume. We're interested in an optimized can with max volume. Now, we're going to have a secondary equation, and that will be surface area. Our secondary equation is surface area. We know, for reasons we've already talked about, that the surface area will be 2 pi r squared plus 2 pi r h. And we found that the surface area that we have to work with is 276.5 cm cubed. Our primary equation, and how do we know this is the primary equation? It is the equation that we want to optimize or maximize is volume, and we saw that that is equal to pi r squared h. And we want to optimize this volume equation. If we want to optimize or maximize the volume equation, we know that if we drew volume as a function of some variable, at some point it's going to have a maximum. And we know that the maximum has a first derivative equal to 0. That's the slope of the tangent line. And because it's concave down, at this particular point, the second derivative will be negative to give us concave down. Volume here is a function of what? As a function of the radius in my little graph here. But my problem is in this equation, I have volume in terms of both R and H. And so we need to find a way to write volume in terms of one variable. Thank goodness that we have this secondary equation, because now we can isolate the secondary equation for H. If I'm trying to solve for H, I can subtract 2 pi r squared from both sides to give me 2 pi r h is equal to 276.5 minus 2 pi r squared, and then divide both sides by 2 pi r to give me h is equal to 276.5 minus 2 pi r squared divided by 2 pi r. Now, this is what h is equal to from my secondary or constraint equation. I call the secondary equation the constraint equation because we are constrained to using just 276.5 centimeters squared of material. The beauty of this now is every time I see H, I can make this substitution. So now I can say the volume is equal to pi r squared times whatever H is equal to. From my secondary equation, I know that's the constraining volume, the constraining surface area, 276.5 cm squared minus 2 pi r squared divided by 2 pi r. Now, because I have multiplication here, I can cancel the pi with the pi and the r with one of the r's, and then distribute that r to the numerator. So volume is equal to 276.5. When I distribute this r, I get r minus, I have to distribute it again, 2 pi r cubed all over, well, what's remaining in the denominator is 2. Using our ideas from algebra, we know this single denominator can divide into both of these to give us 276.5 divided by 2, which is 138.25 r minus, if I divide 2 into 2 pi r cubed, I get pi r cubed. What have I done here? I have successfully written volume in terms of one variable, and that variable is r. I can see that what I need to do is find the first derivative of v and set it equal to 0 to find my critical values, to figure out what is this r value here that will give me a maximum volume. So v prime is equal to multiply and subtract 138.25 minus multiply and subtract 3 pi r squared. And we're going to set that equal to 0, subtract 138.25 from both sides, and we get 3 pi r squared equals negative 138.25. Now I'll divide both sides by negative 3 pi. And then what I'll do, well, that will become positive and positive. And then what I'll do is I'll take the square root of both sides. So I'll get 138.25 divided by, I'm going to put this in parentheses in the denominator to remind myself when I take the division, I have to tell my calculator my whole denominator is 3 times pi. So you can see that these two parentheses are super important to us in order to get the right answer. Now, look at R values. Look at our domain. R values in our conceivable domain are only going to be positive because that represents the radius. We're not going to get a negative radius. So when I do this and I put this in my calculator, remembering to put parentheses around my denominator, I get about 3.8 centimeters. What is this? This is my optimized radius. I think that this is radius. I think that this is going to give me a maximum volume. Of course, in order to have a maximum volume at this critical value, what I'm saying here is I believe that this 3.8 will give me my maximum volume. What I'm going to do is make sure that the second derivative is in fact negative when my R value is 3.8. So my V double prime, if I use this here as my V prime, then my V double prime is, remember, constants go to zero when we take the derivative, even if we're taking the derivative of the derivative, and we're going to have multiply and subtract negative 6 pi R. Now, V double prime, when our input is 3.8, will be negative 6 pi times 3.8. And we can plainly see this is negative, which means concave down, which means R equals 3.8 is a relative maximum, because concave down gives us a maximum value at the top of that mountain there. To my secondary equation, which I solved for H, so I could substitute it into my primary equation, and this is what I came up with. Well, if this is my H, H is a function of R. So if that's the case, we can say H, when R is 3.8, will be 276.5 minus 2 pi 3.8 squared divided by 2 pi times 3.8. We're substituting 3.8, our optimized radius, into our H equation to find our optimized height, which is 7.78, which I will round to the nearest tenth. So what have I just found? After I found my optimized R value, I substituted into my H equation to get, I'll label this. This is my optimized height. Notice that two cans should have the same surface area and get more volume from the optimized can. By doing some calculus, we found that the optimized radius was 3.8 centimeters and the optimized height was 7.8 centimeters. So our optimized volume is pi r squared h. And now we're going to substitute in that 3.8 squared for our radius squared and our 7.8 for our optimized height. And when we do this, we get 353.8 centimeters cubed. Now, what we want to do is compare our optimized volume from a can with the same amount of material. That's so important that we have the same amount of material, that same surface area, 276.5 centimeters cubed. And we want to consider, well, what percent optimized was our original can? The original can had 251.3 centimeters cubed of volume, and our optimized can has 353.8 centimeters cubed of volume. I'm going to multiply this by 100%, and I get 71.0% optimized. So now what I do is I go to Desmos.com, and I put in my volume equation in terms of R. Notice that's that 138.25 R minus pi R cubed. That's volume as a function of R. Look what happens to the very maximum point here if I consider only positive R's. At the very maximum, I've got an R value of 3.83. Remember, when we did our calculus, we found 3.8 and we rounded it to 3.8. And then the maximum volume based on this equation is 352.997 cm cubed. And when we used 3.8, we got 353.8 cm cubed. So you can see that the values are slightly off because Desmos used the full 3.83, which we could have used, but we just did it to the nearest tenth. Notice now what I did is I did parentheses 2.0. That was the original can's radius, comma, 251.3. And I clicked that I wanted that labeled. Look at that point. That point is way down here in green. I still have to keep on going to find it. You can see, maybe it's easier if I do this. You can see there is our 251.3. And if I get them both in the same, viewing window, you can see that, there it is, that's what I was looking for, that to pop over to the other side here. You can see that My graph, this point of the original, is 71% of the way to the peak. And I want you to construct a better can. Given the same surface area, that's our constraint from our secondary equation, I want you now to physically construct and decorate very nicely your optimized can.